Swayam Prabha. Digital India. Educated India.
In this course, we have seen evolution of data science, where big data come from. Then we talked about various aspects of mathematical basis, linear vector space, matrices, concepts from multivariate calculus, and concepts from finite dimensional optimization. There are two more tools which I have not covered: basic statistics and basic probability theory. I'm assuming that you are familiar with basic probability theory. Later, I'm going to be talking about basic estimation techniques. So we have covered a lot of topics. Now I'm going to go for the third set of topics called modeling. Please remember, what is one of the fundamental tasks in data science? You go from data to model. Once you have a model, using the data gives rise to the model. The model has unknown parameters. I'm going to use the very same data to be able to estimate the parameters of the model. I'm going to illustrate every aspect of data science, the mathematical aspects of it, in this course. Now we have done enough of mathematics. Of course, we can continue to do mathematics for the next 2 years. It makes no sense. We need to be, so the question comes in, do you learn all the mathematics you need and then start doing application? No. You learn basic mathematics and start the application. Go as far as you can. If you get stumbled, then come back to mathematics, learn the things and push your application forward. So I believe we have the basic set of skills so far to get started with attacking modeling problems. So what is you remember the first lecture on data simulation in evolution of data science? I talked about model comes in various shapes and forms: static model, deterministic model, linear model. Then we talked about inverse problem, forward problem. Now I'm going to talk about static, deterministic, linear, inverse problem, which is well-posed. Well-posed problem are those for which the solution is guaranteed and I have a pathway to find the solution. Ill-posed problems are very difficult to solve. A problem can be ill-posed if the solution doesn't exist. The problem may be ill-posed if there are many solutions. So ill-posed versus well-posed. So first you need to be able to talk about well-posed problems. In general, inverse problems are always ill-posed. So, and I'm going to consider a special class of well-posed inverse problems. And you also now know what is an inverse problem, what is a forward problem, what is static, what is dynamic, what is linear. Are you with me? I have introduced all these terms. So now I'm going to start synthesizing and using all the tools to be able to establish the basic ideas that we expressed in our very first lecture, evolution of data science. With me? So I'm going to state a problem. I'm going to start with the data. So I'm going to go from data to model. So I'm going to consider a problem of a particle moving in a straight line. So your particle is moving in a straight line. The particle started from some place. The original space is Z0. I don't know where it got started. It is traveling at a velocity which is constant. I don't know the velocity. So the initial position and velocity are not known. but I can observe the position of the particle. So I now know, I have been told the particle is moving in a straight line. It started at z0. It is traveling at the velocity v. I want to find z0. I want to find v. I want to be able to collect observations of this. You can think of this as an astronomical problem, right? Earth is moving around the sun. I don't know when it got started, but I want to be able to find the velocity. You can think of this to the astronomical problem. So what do? I am going to employ people at distances d1, z2, zm. This is z1, this is z2, this is zm. I have located people along the line. I'm asking the person at this position to register the time t1 at which the object crosses that point. So t1 is the time it reaches the position z1, t2 is the time it reaches the position z2, tm is the time it reaches the position zm. So I observe all these things and tabulate them. So this is very similar to astronomers registering the position and time of various objects. Are you with me? So that's the problem we got started with. So given the pair Ti, Zi, I is equal to 1 to m, my job is to be able to estimate Z0 and V. With me? That's the problem. So this is the given data. So Z0 is the unknown, V is the unknown, this is the known. I want to first relate the known to the unknown. That's where the model comes in. This model, I picked it to be a very simple physics model. From physics, I do know the position Zi must be equal to Z0 plus Vti. Understand? That comes from the basic physics. In Ti units of time, it would have traveled Vti. It started at the position Z0. So the position at time T1, which is Z1, which is Z0 plus Vt1, and so on. So this is the model. This model is a static model. With me? This model is a static model. And there are m such a relation. I'm going to collect all the m such a relation and denote it as the matrix vector form. Let Z be a vector, which is Z1 to Zm. Consider the matrix with two columns, the first element all 1, second element T1, T2, Ti, Tm. Please understand, T1, T2, Ti, Tm, I know. Z1, Z2, Zi, Zm, I know. Ones, I know. So what is not known? Z0 V. So look at that. Z1 is equal to Z0 plus Vt1. Zi is equal to Z0 plus Vti. I can express this Z is equal to h of x, where h is the matrix. This matrix is a m by 2 matrix. This unknown vector x is a 2 vector. With me? So the equation 3 is a linear model. It's a static model. It's a deterministic model because there is no noise. I'm assuming I'm able to measure T1, Z1, T2, Z2 perfectly without errors. With me? That's right. So when I say it's 11:20, is it exactly 11:20? No. 11:20 happened some 30 seconds ago. The 11:21 becomes only after 60 seconds. So when I say 11:20, it is 11:20 plus 28 seconds. We forget that 28 seconds, that's an error. With me? So no matter how accurate you are, times are measured only approximately. Positions, you cannot measure positions precisely. That's always an error. So if you consider errors, the model becomes stochastic. If you don't consider errors, the model becomes deterministic. There is no noise associated with it. That's the assumption I'm making. That's why it's deterministic. So it's deterministic, it is static, it is linear. It is the form Z is equal to h of x. Given Z and h, I want to find x. Now I'm going to formulate the problem, general case. In general, my Z could be a m vector. My x could be a n vector. Please understand, only to motivate, I assume the two unknowns, right? In general, that could be n unknowns. M is the amount of data, n is the number of unknowns. Z, the set of observation vector, so that's called the observation space. Z is called the observation space, the m-dimensional space. X is the unknown vector, X is called the model space. H is the relation that connects the model space to the observation space. It maps the vectors X into Z through the relation X is equal to, Z is equal to H of X. H transpose is a map that goes from Rm to Rn, which we have talked about it yesterday. So if xi is a point in Rm, if eta is a point in Rn, eta is equal to H transpose xi. So H is a bridge, H transpose is the reverse bridge. Everybody plays. H is the bridge that takes you from Rm to Rm. H transpose is the bridge that takes from Rm to Rn. Model space, observation space, the map that relates the model space to observation space. These are all fundamentals in data science. Observation. So I am trying to reside in the observation space. I want to be able to infer something in the model space. The guy who connects the model space to observation space is the model matrix H. H sometimes is called the design matrix. If this design is a well-designed problem, it's called a well-posed problem. If design has errors or defects in it, it's called the ill-posed problem. Where and how the defects can come in, we will see as we go by. Problem formulation. So what did I have done? I collected the data, I built the model. The problem I assumed is very simple. The model is a causal model. I calculated the causal model using the basic physics. With me? In the case of Kepler, what is the model, causal model he wanted to find? It's the ellipse. In the case of Newton, what is the causal model he wanted to talk about? The position described by the solution of a differential equation. With me? Model, causal model, deterministic model. So this looks like H of X is equal to Z. This is the linear equation. If m is equal to n, please understand, n is the number of unknowns, m is the number of knowns. If m is equal to n and H is non-singular, that means if the matrix is square and non-singular, I can compute the solution to be this, the classical solution. But never m and n will be equal. When m is not equal to n, H is the rectangular matrix. The standard notions of non-singularity does not apply to rectangular matrices. The determinant of a rectangular matrix is undefined. So the concept of singularity, non-singularity is purely in the world of square but not extended to rectangular matrices. So two cases arise, m is greater than n, m is less than n. When m is greater than n, I call it over-determined system. Over-determined system means what? I have more observation than the number of unknowns. M is less than n, under-determined case means what? I have less number of observation than the number of unknowns. Which corresponds to what? In chemical engineering department, you folks may set up an experiment, it may take 1 year. Once you set up the experiment, you can grind it 24/7. You can get several PhDs. You can get observations very easily after setting it up. With me? So when the cost of finding the observation is smaller, you collect more information, you collect more observation. When the cost of collecting observation is more, you may not afford to spend a lot of money to collect more observation, you collect less observation. So the m greater than n, m less than n depends on the cost of observation. For example, in meteorology, satellite came only in the 1950s. So before 1950s, the amount of observation that meteorologists can do over the earth is very limited. We are only very partial information. Satellites, they are $250 million, $250 million. I'm sorry, yeah, $250 million, $250 million you have to pay for a satellite. Government pays for it. Once the government pays for it, satellite keeps staring at the earth 24/7. The amount of volume of data satellite generates is enormous. Radar is also very expensive, but once you have a radar that continuously watches the sky and spits large amount of information, observations. Let me tell you a situation where m must be less than n. Suppose there is a mountain. The mountain is supposed to contain gold. I would like to be able to excavate the gold. I want to be able to estimate how many tons of gold are in that mountain. Because excavating gold is very expensive proposition. So how do you estimate the amount of gold hidden in the mountain? You have to drill holes at several places. And geologists know how to evaluate the volume. To drill one hole for 2 miles, it takes $10 million today. So even for the richest mining companies, they may not be able to afford too many holes. So using the information from a small number of holes, they have to estimate the amount of gold buried in a given mountain to be able to make a decision. Yes, it is worthwhile going to do the mining. No, it is not going to be. It is not going to be feasible. With me? That's right. Hey, these are inverse problems. How do you decide how much of mica is in this mine? How do you decide how much of coal is in this mine? How do you decide how much of petroleum is in this well? How do you decide how much of aluminum I can get out of this if I did mining? Everybody in my place. These are problems of estimation. They are inverse problems. I have to estimate the unknown based on few observations. With me? So now I'm going to mathematically, now that I have formulated the problem, I want to be able to understand the difficulty in solving these problems using simple ideas. So let m be equal to 3, n is equal to 2. Let's consider the same problem, h 1, 1, 1, 1, 2, 3. Here the columns of h are linearly independent. With me? The span of h is a 2D plane, which is a subset of R3. We all know that, right? One vector decide a one-dimensional subspace. Two vectors together define a two-dimensional plane or a subspace. Three vectors linearly independent define a three-dimensional subspace. There are three vectors. I have two vectors in R3. These two vectors define a subspace, which is the plane. The plane is a subset of R3. Now let's consider z is equal to 0, 1, 2. With me? Hey, look at that now. What am I interested in? Z is equal to h of x. This z is such that I can express this as a linear combination of the columns. Minus 1 times this plus 1 times that becomes z. That means the z belongs to the span of h. You remember the span we talked about? Span is the linear combinations of the columns of h. That's a subspace. Z lies in the subspace. So if z lies in the subspace of this, which is the span of h, the x is a unique value. X is equal to minus 1, 1. That means I can solve z is equal to h of x for a unique x if and only if z lies in the span of the columns of h. Are you all with me? That's right. That's a fundamental idea here. But more often than not, z may not lie on the span of h. Why? Z is the observation I collect. The observations are collected may have noise. My h is defined by 1, 1, 1, 1, t1, t2, t3. Are you with me? So the observations I collected and the times I chose, the errors in the problem may be such that z may not belong to the span of h. That's what's going to happen all the time. So recall, the columns of h are defined by the mathematical model. The column z are observation, come from the real world of measurements. Generally, the observation have noise embedded in them, and the models are only approximations of reality. Hence, more often, not more often than not, z does not belong to the span of h. in such a case, z is equal to h of x does not have a solution. Solution means what? In algebra, the left hand side must be equal to the right hand side. If I can't make the left hand side equal to the right hand side, I can say no solution. So when z does not lie in the span of h, there can be no solution. More often than not, in practice, in the equation z is equal to h of x, z will not be part of span of h. It will be outside of that. So in such a case, what happens? So what am I going to consider now? I am going to consider a case where z does not belong to the span of h. That's the reality. That's what's going to happen. So z is equal to h of x. Now I have three equations and two unknowns. Everybody, m is the number of equations, n is the number of unknowns. So how do you solve three equations and two unknowns? You can solve the first two, assuming the determinant is not 0, and to substitute the solution in the third. If you solve the first two and substitute in the third need not satisfy the solution for the first two. Why? He did not participate in the solution process. If you took any two and solve and substitute in the third, the solution of any two need not satisfy the third. That's the general case. So what does it mean? There is no x for which z is equal to h of x is true. That means there is no solution. Therefore, when m is greater than n, so in this case, I'm just trying to compute. So if you took the first two, the solution for the first two is given by this. I want you to check, and that does not satisfy the third. Verify that the solution of any two does not satisfy the remaining equation. In this sense, there is no solution to z is equal to h of x when m is greater than n, equal to n. I'm sorry, m is greater than n, not equal to, sorry. All of it? So in the overdetermined case, in general, there is no solution. Such a case is called inconsistent case. Inconsistent means what? If you solve any two, it does not satisfy the other. They are not mutually consistent. They are not mutually consistent. That means there does not exist a solution x1, there does not exist a value of the vector x that satisfies all the equations simultaneously. With me? So overdetermined system is always an inconsistent case. Now let's come to underdetermined case. M is 2, n is 3. I have two equations and three unknowns. I can rewrite this as two equations and by kicking x3 to the right hand side. x3, I don't know what it is. It can take any value. So if the determinant of this is non-zero, you can readily see, right? The determinant is 1, 2, 1, 4. Everybody, right hand side. So this system is solvable. If I put x3 is equal to 0, I get one solution. If I took x3 is equal to 1, I get one solution. If I took x3 equal to -1, I get another solution. So for every value of x3, I get a solution x1 and x2. Therefore, x1 is a function of x3, x2 is a function of x3. So for every x3 belonging to R, there is a solution. There are infinitely many x3. Therefore, z is equal to h of x has infinitely many solutions, which is x3, x1, x3, x2, x3. Hence, there is no uniqueness when m is less than n. So there are three cases. So m, n, that's what this diagram says. M, n, m greater than n, it is overdetermined. If I assume the rank of h is n, in this case, it's full rank, right? The rank of h is less than the minimum of m and n. If it is equal to the minimum of m and n, is full rank. M is greater than n, the minimum is n, the rank is n, this is a full rank. So, overdetermined system, I am assuming the rank to be full, yet the system is inconsistent and there is no solution. That's the problem we want to solve. When m is equal to n, rank of h is n, there is a unique solution. When m is less than n, is underdetermined. Here again, I am going to assume my rank is full, that is equal to m, because m is the minimum of the two. There are infinitely many solutions, there is no unique solution. This is something we have already learned in linear algebra. These are the two things that we need to learn. So, thus we need to generalize the concept of solution in the two extreme cases, m is greater than n, m is less than n. This notion of a generalized solution is called the least square solution. Hey, it's a good oral exam question. You talk about your methods and other thing. I solved the method of least squares. If somebody asks you a very simple solution, please explain the difference between solution and the least square solution. That's the answer. Okay? Least square solution is a generalized concept of solution. To say I have solved the problem is to say left hand side is equal to the right hand side. The generalized solution, the least square solution, admits the possibility of left hand side not equal to the right hand side, yet I am going to call it a solution. So in what sense the least square solution differs from the classical word solution where the left hand side is equal to the right hand side? That's the theory of least squares. All of it me? That's right. It is about that theory which is the modeling part. So I went from data to model. I have two parameters that are unknown. I'm now going to use the data to be able to estimate the parameters of the model. This is called the data assimilation step. Everybody. So I first solve the inverse problem of data to model using the physics. Now I'm going to combine the model of the data to be able to estimate the parameters using least squares. We are doing exactly what happened in astronomy during the time of Gauss, except that the problem is different. So what am I going to do? I'm going to, in this modeling part, I'm going to describe the grand theory of least squares. This is called multivariate regression, least squares theory. It is also a typical problem in inverse theory or inverse problems. It comes under various names. It's also called the estimation problem, inverse problem, estimation problem, least squares problem, regression problem, have been around for hundreds of years. And that constitutes the core of data science. So I want to relate the past to the present, what constitute the components in data science. I hope you are all with me. Least squares can be formulated in one of two ways. One is unweighted least squares, another is weighted least squares. So now I'm going to talk about what's called unweighted least square solution when m is greater than n. Okay? I will define unweighted very soon. We keep adding adjectives to describe the various things now. This is R. Let R of is equal to z minus h of x. So I want to make z is equal to h of x. Z is a vector, h of x is a vector. The difference between the vector, the left hand side and right hand side is called residual. The residual is a function of x because z is given, x is given, h is given, z is given, x is. So I want to be able to find an x for which the residual is 0. We just talked about the problem of no such x exists if m is greater than n. With me? So I'm now going to be talking about the properties of this residual vector. This is essentially R. This is the lowercase r, like that, right? You all know that. This is the same R as that. Recall, when m is greater than n, there is no x for which Rx is 0. So what's a good compromise? Ideally, Rx must be 0. Rx is 0 means what? It's a 0 vector. The length of the 0 vector is 0. So what is the next best thing I can look for? I want to find an x such that the length of the vector Rx is minimum. So a least square solution seeks to find the value of x for which the residual is not 0, but its length is as low as possible minimum. Are you with me? If the minimum value happens to be 0, so be it. So I'm trying to generalize the solution from Rx being 0 to a vector whose length is minimum as a function of x. All of it in place? You all have an aha? It is in that sense, it is a generalized solution. So as a compromise, we seek x for which the vector Rx has a minimum length. Minimum length is the same as square of the length must be minimum. So to this end, what do? I want to be able to minimize the length. Now look at this now. What does the word minimum mean? Optimization. So I want to be able to convert the problem into one of optimization. I have already talked about the transition from model to estimation to optimization. The model estimation now recasts as an optimization problem. Optimization is one of finding the x for which the length of the residual vector is minimum. Optimization, multivariate optimization, sneaks its way through in the least square formulation. So to this end, what do? I need to develop an objective function. My objective function is called f of x. So minimizing the length is the same as minimizing the square of the length. Everybody? To compute the length, I have to take the square root. With me? The length of the vector is the square root of the sum of the square. Why bother about square root? In the differentiation, it will cause problems, right? So I'm going to minimize the square of the length. So I'm going to define f of x as square of the length, which is Rx transpose Rx, which is the sum of Ri squared. So what is this? This is the square of the norm of the residual. Then what is Ri? Ri is Zi minus the ith row times x. We all know what that one is. It's the ith component of the residual vector. So f of x is the sum of the squares of the component of the residual vector. The sum of the square of the component of the residual vector. Least square, the square in least squares refers to this square. Least, I want to find the minimum. So least square is representing minimizing the sum of the squares of the component of the residual vector. Therefore, the x that minimizes f of x is called the least square solution. All of it may? That's right. What is least square? Why least square is different from the ordinary formulation? Why we want least squares? Because the problem does not admit a solution. I want to be able to extend the notion of the solution. I want to be able to extend the notion of my tools to solve problems. So by giving up on the concept of solution, I'm trying to expand the methodology for solving problems. Are you all with me? That's right. You need to give something to get something. That's life. What is now? It's mathematics. Optimization takes over. So we collected data, we built the model, we analyzed the model to see whether the solution exists or not. We made a compromise. We converted the problem into one where which I can solve the problem to get not the solution but the least square solution. Now I want to move forward to be able to find the least square solution. All of it, me? Am I using every one of the ideas that I have introduced in the course so far? That's right. Now I'm going to go back to minimization. So least squares method, m greater than n, f of x is equal to Rx transpose Rx. Rx is equal to z minus h of x. Everybody please. That is z minus h of x transpose z minus h of x. I'm going to use several formulas now. A plus B transpose is equal to A transpose plus B transpose. You remember we saw yesterday. AB transpose is equal to B transpose A transpose. These are the two formulas I need. So you distribute the transpose in here. From there you get this. You apply the transpose in here as x transpose h transpose. This is A plus B times C plus D. I'm going to get 4 terms. Everybody, you should be able to multiply that. Matrix algebra, everybody, you should be thorough with that. Now, each of these things are constants. So what is this f? This f is a function from Rn to R because x is a n vector. It is a scalar valued function of a vector. It's the functional. It's the cost functional. I want to be able to minimize this cost functional. This cost functional is a quadratic function in x. Everybody. So if I can show that the matrix H transpose H is symmetric and positive definite, this must have a unique minimum. All of it may please? I'm just trying to open up all the things now. But before I do that, I want to simplify. So every quantity is a scalar. What are the properties of scalar? 2 transpose is 2. A transpose is A when it's a scalar, right? So Z transpose H of X is a scalar. It is equal to its own transpose. The transpose of the product is the product that the transpose has taken the reverse order is equal to this. Therefore, the transpose of this is equal to this. Though these two terms are equal, so I can drop one of them by introducing a 2 here. So this is the function I want to minimize. How does this function looks like? This function looks like X transpose AX minus B transpose X plus C. This is the C part. With me? This is the linear part. This is the quadratic part. All of it with me? That's right. Find an X that minimizes f of X and sub. Find an X that minimizes f of X and sub. Now you see, I have utilized every result from the previous lectures here. Many of the lectures in here. So if H is a full rank matrix, H transpose H, that's a Gramian. You remember I have introduced the Gramian? H transpose H. So if I have a H, I have H transpose H, H transpose. If this is m by n, this must be n by n, this must be m by m. I am assuming n less than m. So this is called the smaller Gramian. This is called the larger Gramian. Everybody. The Gramian is such that it's symmetric. Why? If you took the transpose of it, it is equal to itself. That means it's symmetric. Everybody? I want this to be positive definite, this matrix to be positive definite. I'm going to check that now. So consider the quadratic term. X transpose H of X, X transpose H of X. Do you remember I can rewrite this as X transpose H transpose. So what is that I do? Please understand, that's what's called associativity. If I say A, B, C, which is equal to AB times C, which is equal to A times BC, matrix expressions are associative. So I can associate like this. If I associate like this, this term is equal to H of transpose. This is equal to H of X. That is equal to H of X square. Namata is H of X square. All of it me? That's right. That's right. Now, I want this to be positive definite. If I want this to be positive definite means what? This H of X is 0 only when X is 0. The norm is not 0 when H of X is not 0. But what is H of X? H of X is simply linear combination of the columns of H. Everybody? Are you all with me now? So under what condition H of X will not be 0? If the columns of H are linearly independent, for no X, H of X will be 0. Therefore, H being a full rank is a necessary condition for this quadratic function to be symmetric and positive definite. Therefore, X transpose H is greater than 0 when X is not 0, only when X is 0. H transpose H is positive definite. So, where ultimate responsibility lies, it depends on the rank of H. So, by forcing the rank of H to be full, who decides the rank of H? You. Go back to the problem of the particle moving in a straight line. 1, 1, 1, T1, T2, T3. If all the T's are equal, they are linearly dependent. So what does it say? If you want to solve this problem, you should have observation at least at 2 distinct times. If you make all the observations at the same time, your problem is screwed up. Ill-posed. If it is ill-posed means because of what? The rank becomes less than the minimum. All of you? So if the problem poses headache for you, it's because of you. Don't blame anybody else. So you need to make sure that your problem is well posed. One of the conditions for being well posed is that the columns of H must be linearly independent. H must be full rank. Now I want to talk a little bit about unweighted. Suppose I'm defining f of x to be Rx transpose W times R of x, where W is a matrix which is m by n. And if I make W to be a diagonal matrix W1, W2, Wn. Please understand. So what does this now become? This becomes summation Wi Ri square of x. I is equal to 1 to m. Are you all with me now? So if you go back in here, it is simply the sum of the square of the residual. Here, I am trying to weight them. Where did I? Yeah, here I am trying to weight them in here. If all the weights are equal, democracy, every vote counts the same value, whether you are a president or a peon. If the weights are not equal, means what? I am giving more weight to some components than others. Let's take an organization. The head of an organization has more weight than the dean. The dean has more weight than the head of the department. Head of the department has more weight than the faculty. Are you with me? That's right. So in decision making in any organization, the decision is always a weighted decision. Faculty give input, dean gives input, director makes the decision. Are you with me? How he uses the input from the faculty, the dean, in making his decision, he probably won't divulge this to you, but he has his own way of thinking, right? He has other constraints to make a decision. Weighted decision, unweighted decision. Unweighted decision is pure democracy. Weighted decision means some people have more value than others. In other words, the opinion of some people have more value than others. An organization cannot be purely democratic, right? I don't know whether you have heard a proverb. If you ask 6 economists, there are 7 opinions. What is the 7th opinion? They agree not to agree. So if everybody has their own opinion, an institution cannot run. So in an institution, for it to run, you need to have some kind of a weighted decision process. But when it comes to country electing people, I'm interested in pure democracy. Every vote counts the same. With me? Weighted decision, unweighted decision. Weighted least squares, unweighted least squares. The unweighted least square is a special case of weighted least square where all the weights are same. If all the weights are same, I can assume this to be unity by scaling it. Are you all with me? That's right. That's the difference between weighted and unweighted. There may be situations where you may want to be able to weight them. So there is one case where weighted decision becomes important. When the observations have noise, there is a very natural way to weight the least square criterion to take into account the properties of the noise. We will talk about it a little later. So at this stage, I simply talked about weighted and weighted. So what is the problem on hand now? I have now shown that this problem, minimization problem, has a unique solution if the rank of H is full. Everybody. So what is the idea here? The overdetermined unweighted least square problem, where there is larger number of observations than the parameters. The problem is well posed when the matrix H is of full rank. That's it. That's the result. Now what do? I simply need to use the tools from optimization theory. I don't have to work too hard now. What do I do? Take the gradient equal to 0. Compute the Hessian, check whether it is positive definite. You get the solution. All of you? Come on guys, please nod your head. This is for us, this is for now. So refer to 7. Refer to 7, that is the objective function. I have now argued the objective function is the unique minimum. I want to compute the gradient of Hessian. Refer to 7. There are 3 terms. The gradient of the sum is the sum of the gradients. The gradient of ZZ transpose is 0. The Hessian of ZZ transpose is 0. The gradient of 2 times Z transpose H is the, okay, so now I'm going to give you a pathway now. So 2 times Z transpose H of X, I'm going to rewrite as A transpose X, where A transpose is equal to 2 times Z transpose H, where A is equal to 2 times H transpose Z. Do all of us see that, please? Hello? The gradient of this equal to A, and what is A? A is equal to 2 times H transpose Z. All of you? And the Hessian of that is 0. The Hessian of that is 0 because a linear function. A linear function does not have a second derivative. The third quantity, the gradient of this is 2 times H transpose H. You remember? X, the gradient of X transpose AX is 2AX. I'm using all the formula. The Hessian is positive definite. The Hessian 0, the total Hessian is 2H transpose H, so second order condition is satisfied. I need to be able to combine the gradient. So the combined gradient is given by this equation. Everybody with me, gradient of F. I have to equate this to 0. The gradient is essentially SPD. Therefore, I have to solve the gradient equation. The least square solution is the solution of this set of equation. And this set of equation, when you cancel 2 and put that, you get a linear system. H transpose Hx is equal to H transpose Z. So this is a linear system with a n by n matrix. So to solve Z is equal to H of X, which is the m by n matrix, I convert this into solving a n by n matrix. This equation is called normal equation. This is a special kind of equation where the matrix of the equation is symmetric and positive definite matrix. Everybody. In general, Ax is equal to B, A is non-singular, is all what you need. But I'm given more. I'm given the symmetric and positive definite. How many of you have seen normal equations? You said you did layer optimization. That's right. Are you with me? So these are very useful concepts. So I am called upon to solve this linear symmetric positive definite system. Now I already know H transpose H symmetric and positive definite. If it is symmetric and positive definite, it is automatically non-singular. Everybody. Therefore, I can write the least square solution to be H transpose H inverse H transpose Z. I can collect all these matrices and call it H plus. Now let's look at this now. If I'm going to solve this, I say X is equal to A inverse B. If I'm going to solve Z is equal to H of X, I'm going to solve D square is equal to H transpose H inverse H transpose Z. This can be replaced by H plus Z. With me? So now does this look like this? So H plus replaces A inverse. Therefore, we call H plus the generalized inverse of H. This is called Moore-Penrose generalized inverse. We talked about it yesterday. You remember that? That's right. That's right. So what is that least square theory helps you? It helps you to extend the notion of a solution. It helps you to extend the notion of a generalized inverse of a matrix. So I am trying to generalize the solution. I am trying to generalize the inverse of matrices. With me? From square to rectangular. That means I am expanding the mathematical reach. The Hessian is already symmetric and positive definite. And if the Hessian is symmetric and positive definite, f of x is convex function. So I have a quadratic convex function to be minimized. It's an unconstrained minimization. I want you to understand that now. There's no constraint here, right? So solving an overdetermined least square problem gives unweighted overdetermined least square problem gives rise to unconstrained minimization, where you compute the gradient equal to 0, you compute the Hessian, check it to be positive definite, and you get a solution. In that process, you also get to generalize the notion of inverse of matrices from square to rectangle, the notion of a generalized inverse. Here I want to tell you, which I have already talked about in great detail in the last class when I talked about matrices. With me? There are several different ways in which you can generalize the inverse of matrices. There are 300-page books written simply on generalized inverses. With me? So have we solved the least square problem? So if you give me z is equal to h of x, the solution is obtained by solving the normal equation. I can write the solution to be like this, h plus z, but computationally I need to compute that, right? I will talk about the computational solution a little later. But here I am trying to develop the theory. Computation process comes only after establishing a good theory. A good theory precedes every algorithm. With me? Are you all with me now? That means I converted one problem to another problem. I convert the linear least square problem to solving a system of linear equations. And this we did it by walking through, by transforming the problem into an optimization problem as an unconstrained optimization problem. You see the beauty of it? Interconnection, various things. So if I know the minimum solution, I can compute the minimum residual. You remember what we said? I want to find an x such which the length of the residual is minimum. So I want to be able to compute the length of that residual. So Rx is equal to z minus h of x, or XLS is equal to z minus h LS. So if you substitute the value of XLS from here to here, I get the minimum value of the residual. So what is the minimum value of the residual? This is equal to z minus H transpose H inverse H transpose Z. Z is a common factor. So I have this matrix times Z. Are you with me? And this is never 0. And this is never 0. All of it with me? This is never 0. So herein lies the difference between the classical solution where Rx is 0 and the least square solution where Rxl is not 0 for the overdetermined case. So that's the residual. So what is the minimum value of the function itself? The minimum value of the function is Rx square. So I need to substitute here x is equal to XLS. If I did that, that's equal to this. So this is the minimum value of the function. This is the minimum value of the residual. The minimizer itself is given by XLS. So I have XLS minimum solution. I have RXLS, the minimum residual. I have f of XLS, which is the minimum value of the objective function. Minimum value of the sum of the square errors. Everybody? I want to illustrate it by the straight line problem. I want to solve the problem using this method. That's what we started, right? That's right. I want to give expressions. So H is this. My H transpose is this. Everybody? My H transpose Z is this. So I'm now going to write H transpose Hx is equal to H transpose Z. So H transpose, that is the matrix. This is the right hand side. If you divide a matrix by M means I divide every element of it, vector every element of it, both left hand side and right hand side. If I did that, what do I have? This becomes 1, this becomes 1 over m summation, 1 over m summation, 1 over m t square, 1 over m zi, 1 over m that. So what am I going to do? I'm going to now introduce new notation. What is t bar? T bar is the average t. What is t square bar? Average of the t squares. What is z bar? Average of z. What is zt bar? Average of the product ZITI. Everybody? So this is T bar, T square bar, Z bar, ZT bar. If I use these symbols, my equation now becomes this. All of you? Please, please, please. So I got a 2 by 2 system. When did you learn to solve 2 by 2 algebraic system? When you were in 8th grade, right? When you were introduced to algebra. You have been doing this for a long time. So you should be able to explicitly compute V star and Z star by solving this 2 by 2 system. Verify the solution is given by this. Are you with me? Hey, what is this called? This is called curve fitting. So T1, T2, Tm, Z1, Z2, Zm, this and there is a curve. This is Z naught. The slope is V. Are you all with me, Bob? That's a regression you have probably used to. That's a regression problem that you are used to. So I generalized it. I computed the solution, and I computed the minimum value of the sum of the squares. I also computed what's called the RMS error. What is RMS error? So let's look at this now. This is the fitted value. With me? This is the measured value. The difference between the measured value and the fitted value is called the error. The sum of squared errors. That's called SSE. SSE divided by M. That's the average sum of squared errors. Square root of the average sum of squared errors is RMS error. RMS error is a figure of merit. If the RMS error is small, means the line fits the point very closely. If the RMS error large, means the points may lie here and there. The distances are more. All of it, me? That's right. That you are used to. So RMS error is a scalar criterion that helps to measure the quality of the model fit. Quality of the model fit. So I have a numerical example. 1, 2, 3, 4, 1, 3, 3, 2, T bar, T square bar, Z bar, ZT bar. Please don't believe me. I want you to check these solutions. The more you check the solution, you understand it, the better you become. So my V star is this, my Z is that, my fitted model is this, my sum of square error is this, my RMS is this. All of you? That's right. I can also find the minimum by graphical methods. My unknown has only two quantities, Z naught and V, right? So, for the numerical problem that I have here, my f of x is given by this function. This function represents a bowl in 2D. If I cut at various levels, I get contours. So I got contours. Everybody with me, please? So I can solve the problem by graphically, well, maybe the minimum is here. So the contours using MATLAB, the minimum can be found and verified by MATLAB plot as well. With me? And what does this emphasize? This emphasizes that the quadratic function, the cost function is a bowl-shaped curve. It's a bowl that rises like this. Everybody? So the graphical interpretation. Now I would like to come back to weighted least squares. With me? I didn't tell you where, I already talked about where the weighting comes into play. In an organization, every decision is a weighted decision. The general election in a country is unweighted. With me? In a class, the teacher decides the day for the exam. If you ask the class, when do you want to have the exam? Each one will give a date, right? You will never find a solution. So a benign dictatorship is useful for things to run. Everybody? No organization run without leadership. Leadership means what? Getting control. Leadership means what? Giving command, demanding things be done. You need to endow power with somebody so that he will be responsible for making sure everything happens at the right time. With me? That's right. So let M be a symmetric positive definite matrix. I'm going to expand my objective function by introducing a W. Why W is M by M? Please remember that Z is equal to H of X. This is M by N. This is N by 1. This is M by 1. So Z minus H of X is M by 1. So W could be a diagonal matrix with different weights along the diagonal, or W could be in general be a symmetric positive definite matrix. W could be a matrix where all the diagonal elements equal to W. W could be a matrix where all the diagonal elements can be 1. So now what do? I need to compute the gradient. I need to compute the Hessian, equate the gradient to 0, solve for it, check the gradient. Hessian is positive definite. If you did that, you get to this equation. That's called the normal equation. So what is the previous equation? The previous equation was H transpose Hx is equal to H transpose Z. This now becomes that. So that's a W, that's a W. So under the assumption that this matrix is non-singular, this matrix will be non-singular if H is a full rank, because W is already assumed to be SPD. So W is not going to cause any problem. If there's going to be a problem, it will be caused by H. And how do you minimize the problem due to H? Assume he is a full rank. Therefore, the weightlet least squares is obtained by solving this extended normal equation, and the weighted solution is given by that. So going from here to here, there is a certain amount of work. I am going to leave that as a homework problem. That's what we say. Verify that the normal equation in this case. What is that you need to do? You need to compute the gradient. You need to compute the Hessian, equate the gradient to 0, and verify this happens. I have given you all the solutions. You also know all the methods, but please fill it in. If you do all the exercises in this lectures, nobody can touch you. With me? That's right. You can follow any text. So far, I talked about only overdetermined. Underdetermined is a different kind of animal. Why? Their solution did not exist. Here, there are infinitely many solutions. Even though there's only 15 minutes, I can't afford to waste my time. There's a fixed amount of time I have to cover certain topics, so I'm going to continue. Recall, in this case, M is less than N. There are infinitely many solutions. If there are infinitely many solutions, means what? The residual is always 0. If the residual is 0, the residual square is 0. Therefore, the old approach where the sum of the square residual is all 0 is a non-starter for here. Therefore, I cannot use the methodology, the pathway I used for overdetermined for the underdetermined case. I need to cut a new track. Let me know. To solve Ax is equal to B when A is a full rank, I said X is equal to A inverse B. Z is equal to H of X when C is overdetermined case, I described the method, reducing to unconstrained minimization. Now I'm coming to the underdetermined case where there are millions of solutions. Rx is 0. So starting with the sum of square errors is a non-starter. So I have to cut a new path. I want to cut a new method. So I want to get a unique solution. I need to be able to formulate this as a constrained minimization problem using Lagrangian multiplier technique. Are you all with me now? Among all the solutions, I want to pick one particular solution. What is the criteria that you are going to use to pick that particular solution? With me? So I need a new approach. That approach is becoming an equality constraint minimization problem. I'm going to solve the equality constraint minimization problem by Lagrangian multiplier technique. I could also solve it by penalty function technique. Everybody with me, please. I could also solve it by elimination method, but I'm simply going to illustrate it using a Lagrangian multiplier. So reformulation. M is less than N. In physics, we call kinetic energy 1/2 of mv square. If m is 1/2 of v square. So v square, square of the velocity, is considered to be energy in physics. So in mathematics, we consider square of the norm of a vector to represent the energy in the vector x. Mathematics is man-made. God is too busy. He doesn't come and tell you how you should do mathematics. He left it mathematics to your imagination. Are you with me? So much like physicists consider energy, kinetic energy, the analog of kinetic energy is the square of the norm of vectors. The square of the norm of the vector is the square of the length of the vector. That also can be interpreted as the energy in the vector. Therefore, among all x that satisfies z is equal to h of x, I want to find the one which is the minimum norm, minimum energy. That means among all the solutions for the least square problem of an underdetermined case, find the one that has the least energy. You may ask a question, why least energy? If you don't like least energy, you tell me what you want, I will give you the solution. The Lagrangian multiplier technique applies to any condition that you want to put in. To illustrate, I am going to start with the condition, namely minimize the energy. It's a very natural way to formulate underdetermined problem. Everybody? So the constraint must be satisfied. Among all the constraints that satisfies z is equal to h of x, I want to find one for which the energy is minimum. So I have a Lagrangian. We just finished talking about Lagrangian method. So this is the original function to be minimized. This is the constraint z transpose, lambda transpose z minus h of x. Everybody? The Lagrangian multiplier technique tells you how to convert an constraint problem to an unconstrained problem. With me? So I pose this as a constraint problem. I formulate a Lagrangian multiplier problem. Lagrangian multiplier theory tells you how to formulate that problem as an unconstrained problem. So this is an unconstrained problem, two variables x and lambda. So the above is a constraint minimization solved by minimizing the Lagrangian with respect to x and lambda as an unconstrained problem, which we have already seen. So what is that I now need to do? I need to compute the gradient of L with respect to x, gradient of L with respect to lambda, equate them to 0. By forcing the derivative of L with respect to lambda, I am forced the constraint. As we saw already, I can solve this very easily. So the necessary condition for the minimum is given by the gradient of L with respect to x 0, gradient of L with respect to lambda 0. By solving these two equations in two unknowns, x and lambda, we get the optimal x and lambda. So if you compute the gradient with respect to L, it becomes 2x minus h transpose L lambda. If you consider the gradient with respect to lambda, that becomes z minus h of x. Equate them to 0. Z minus h of x, that becomes the equality. I force the equality constraint. Everybody with me, please? So solving 19, I'm going to solve these two system of equations. I'm going to express is equal to 1/2 of h transpose lambda. If x is equal to this, I can substitute in z. So z is equal to 1/2 of h transpose lambda. Now, my h is m by n and m is less than n. So the maximum rank of this is m. Everybody please. H transpose is a m by m matrix. This m by m matrix will be a SPD matrix if the rank of h is equal to m. It's a full rank matrix. So under the condition the full rank matrix, this matrix is symmetric and positive definite. Everybody? H transpose. So earlier I dealt with H transpose H. Here I am dealing with the dual of the H transpose. That is n by n. This is m by m. Therefore, by solving this, if this is the SPD, I can solve this, right? Lambda is equal to 2 times H transpose H inverse Z. Substituting 21 in 20, I get the least square solution to be H transpose H inverse Z. So if H is a full rank, that means the rank is M, it can be verified H transpose is SPD. Everybody? So I can compute the solution in 2 steps. What is the first step? First step is solve H transpose transpose Y is equal to Z. So what will be Y from here? Y is equal to H transpose inverse Z. Then I multiply, find this. That's correct. This gives you the Y that I talked about, and then XLS is simply H transpose Y. So you can find the solution in 2-step processes. Everybody? Now residual, if you substitute H of X in here, look at this now. This is H transpose, the inverse of each other. Their identity, Z minus H is 0. So the least square solution is 0. And this is to be expected since there are infinitely many solutions. The least square solution is a solution. Are you with me? For which the residual is 0. Are you with me now? I am giving you 3 equations in 2 unknowns, solve and verify it is inconsistent. I have 2 equations in 2 unknowns, verify by solving it. And this is the solution given by this. Using MATLAB, plot the contours. Are you all with me now? So you have to do all these things. So in summary, okay, good. Now a few more exercises. Find the minimizer for this and verify this is, we have already talked about that, minimum, the weighted least squares. I want you to be able to do the arithmetic. Now, H plus is the generalized inverse, right? Generalized inverse when M is greater than N is given by this. Generalized inverse when M is less than this is given by that. In both the cases, I am assuming H is a full rank. With me? So take the case of M is equal to H plus is equal to H transpose, H inverse, H transpose. So this will take that. We have already defined what is that to be for H transpose to be a Bode-Penrose inverse. We have talked about the 4 conditions the last time. Any matrix that satisfies these 4 conditions is called generalized inverse of H. Now I have a computed generalized inverse. So you need to be able to verify that these relations are satisfied by this. You also need to verify these relations are satisfied by that. All right? So these are generalized inverses, both of them. You need to be able to solve each of these. Okay, now comes the reference. Louis Lakshmivarahan and all. Do you see my name? Lakshmivarahan is my name. Dynamic data assimilation, a least squares approach. We published a book in 2006. It is based on a course that I taught at the University of Oklahoma at the graduate level starting 1990. We wrote the book 3 times. It is about 700 pages long with 150 pages appendix. It is published by the Cambridge University Press. It is a part of the Encyclopedia in Mathematics in Cambridge University Press. With me? And based on this book, I also have given a set of lectures in NPTEL. I think your library has a copy. All of you? So these lectures are based on my chapter 5. The vector space, matrices, multivariate calculus, everything depends on the appendix to my book. I don't mind giving you a PDF version of my book, my appendix. I'll give it to you free. But somebody needs to give me a thumb drive. Once you give me a thumb drive, I'll upload all the things and you can use them. Are you with me, please? So if you give me a thumb drive, I'll bring it tomorrow. With that, we conclude. We finished it 1 minute earlier. With me? So we are going to continue in this vein of modeling. Probably tomorrow also we will cover several topics related to modeling. So data to model to estimation, inverse problems, estimation problems. Thank you. We will continue next.